Max Planck, born in 1858 inches, the small town of Kiel, Germany, emerged as one of the most brilliant minds of the 19th and 20th centuries, known primarily for his foundational work in quantum theory. However, to truly understand how he became a genius, it's essential to look at his early life, his family background, and the formative years that would shape his future as a scientific pioneer. His family environment played a significant role in fostering his intellectual curiosity and nurturing his passion for learning, and his early education would set the stage for his groundbreaking contributions to physics. Max's family was deeply entrenched in intellectual life, which greatly influenced his upbringing. His father, Johann Planck, was a professor of law at the University of Kiel, and his mother, Emma Patzig, came from a family of distinguished scholars. Growing up in such an academically rich environment, Planck was introduced to the importance of knowledge and intellectual pursuit from an early age. His family, particularly his father, emphasized the value of education and discipline, instilling in him a strong sense of purpose and curiosity. From a young age, Planck demonstrated a keen interest in learning, often engaging in thoughtful conversations with his father and other intellectuals that frequented their household. This environment of intellectual exchange provided the perfect backdrop for his early development. As a child, Planck was quite reserved and introspective, displaying a preference for books and solitary activities over playing with other children. His childhood was marked by an almost obsessive curiosity about the world around him. This curiosity was not just limited to any single area, but extended across various subjects, reflecting his broad intellectual interests. However, his initial interest in science was sparked when he encountered the works of famous scientists and mathematicians, particularly the works of Johannes Kepler, whose ideas about the laws of planetary motion fascinated him, were instrumental in shaping Planck's early passion for science. This exposure to the classical works of science led him to appreciate the structured and mathematical nature of the physical world, providing the first steps toward his future as a theoretical physicist. Max Planck's formal education began at the University of Munich, where he enrolled in 1874 to study physics. His decision to pursue physics came after careful deliberation. Though he had an interest in both mathematics and philosophy, his fascination with the natural world led him to physics as the field that would allow him to explore his intellectual curiosities most thoroughly. At Munich, Planck was exposed to the ideas of some of the leading scientists of the time, including the works of Helmholtz and Kirchhoff. He was especially drawn to the study of thermodynamics, a field that would play a crucial role in his later work on quantum theory. In 1877, Planck transferred to the University of Berlin, where he would study under the tutelage of some of the greatest physicists of the time, including Hermann von Helmholtz and Gustav Kirchhoff. It was here that Planck's passion for scientific inquiry reached its peak. Berlin was at the center of scientific and intellectual activity, providing Planck with the opportunity to engage with some of the brightest minds in Europe. His education in Berlin was not just about gaining knowledge, but also about developing the mindset necessary for groundbreaking scientific research. Planck was particularly captivated by the work of Kirchhoff, who had made significant contributions to the understanding of radiation and heat. Under Kirchhoff's mentorship, Planck developed a deep understanding of the laws of thermodynamics, which would later influence his thinking on energy and the development of quantum theory. At the University of Berlin, Planck encountered the challenges of scientific rigor, which helped shape his intellectual development. The university was known for its demanding academic atmosphere, pushing students to think critically and engage deeply with complex ideas. Planck was no exception. He immersed himself in the rigorous study of theoretical physics, often spending hours poring over equations and scientific texts. His relentless pursuit of knowledge led to his development as an exceptional scholar, a quality that was recognized by his professors and peers. However, it wasn't just the academic challenge that Planck thrived on. He was also deeply motivated by the possibility of making his own contributions to the field of physics. The intense intellectual environment of Berlin encouraged him to think critically and to approach problems with the same level of rigor and precision that would later define his career. Planck's time in Berlin was a period of intellectual transformation, where his understanding of physics matured. He began to engage more deeply with the fundamental principles of physics, particularly the emerging field of thermodynamics. His early work was largely focused on understanding the laws of radiation and heat, but it was also during this period that he began to challenge the prevailing scientific ideas. While many of his contemporaries were focused on the ideas of classical physics, Planck began to explore areas that others had not fully understood, which led him to formulate some of his most influential theories. His time in Berlin laid the groundwork for the later development of quantum theory, as it was here that Planck's mind was first exposed to the complexities of energy and matter, setting the stage for his revolutionary contributions to the scientific world. By the time Planck completed his doctorate in 1879, he had already begun to carve out his own intellectual path. His doctoral thesis, which was centered around the second law of thermodynamics, demonstrated his ability to not only grasp complex scientific ideas, but also to make original contributions to the field. His work was highly regarded by his professors, and his academic journey was off to a promising start. He soon began to publish papers on the laws of thermodynamics and radiation, and his reputation as a young physicist grew. However, it was not just his academic achievements that set him apart. It was his unique approach to scientific inquiry, an ability to question established ideas and seek out novel solutions that would later define his career. Planck's early education and formative experiences, both at home and at university, played a crucial role in shaping the brilliant physicist he would become. His childhood, marked by a deep intellectual curiosity and an academic family environment, laid the foundation for his future success. His years at the University of Munich and the University of Berlin further honed his scientific skills and provided him with the mentorship and intellectual challenges necessary to shape his future as a physicist. These early years of education, filled with intellectual exploration, rigorous study, and groundbreaking mentorship, played a significant role in developing Max Planck into the genius who would revolutionize the field of physics. Through his early life and education, Planck's curiosity, intellectual discipline, and determination to understand the mysteries of the physical world set the stage for the groundbreaking work he would later become famous for. Max Planck's formative years at the University of Munich and later at the University of Berlin were pivotal in shaping his intellectual journey and positioning him as one of the leading physicists of his time. However, it was not merely his education that led to his groundbreaking contributions to physics. His experiences during his academic career, the challenges he faced, and the influential mentors he encountered played a significant role in the development of his unique scientific approach. Through his early academic pursuits, Planck not only absorbed knowledge from his mentors, but also developed his own intellectual framework, which allowed him to challenge conventional ideas in physics and make revolutionary discoveries that would change the course of science. The University of Munich, where Planck initially began his studies, was an essential starting point in his intellectual development. Despite the strong academic background provided by his family, it was at Munich that Planck's fascination with physics grew deeper. As a student, he was initially captivated by the concept of energy conservation and the ideas of thermodynamics, areas that were rapidly gaining prominence in the scientific world at that time. Munich's environment encouraged students to develop a rigorous and systematic approach to scientific problems, something that Planck embraced wholeheartedly. His professors at Munich, although important, were not as directly influential on him as his later mentors in Berlin, but his exposure to the ideas that were circulating at the time laid a solid foundation for his future work. At Munich, Planck began to focus intensely on the study of heat and radiation, which would later become the central themes of his scientific career. His early exposure to the works of German physicists such as Hermann von Helmholtz and Gustav Kirchhoff proved vital in shaping his intellectual trajectory. Helmholtz, in particular, had a profound influence on Planck, as his work on energy conservation and the development of the principle of energy conservation had a lasting impact on Planck's own scientific ideas. At the same time, Kirchhoff's work on black-body radiation and the laws governing the emission of heat provided the theoretical underpinnings for Planck's later work in quantum theory. These early influences were critical in helping Planck formulate his scientific outlook, which combined a deep understanding of classical physics with an awareness that there were gaps and unresolved questions in the field. Planck's academic journey took a pivotal turn when he moved to the University of Berlin in 1877. Berlin at that time was a hub of scientific activity, and the university attracted some of the brightest minds in Europe. It was here that Planck encountered his most important mentors, who would guide him through the formative years of his career. The first of these mentors was Hermann von Helmholtz, whose work on thermodynamics and energy conservation provided a critical framework for Planck's later contributions. Helmholtz's broad understanding of physics, especially in the fields of heat and energy, opened Planck's eyes to the deeper, more complex issues that remained unsolved in the scientific community. Under Helmholtz's guidance, Planck's interest in the laws governing energy and radiation was further refined, leading him to ask deeper questions about the nature of energy itself. Another key influence on Planck during his time in Berlin was Gustav Kirchhoff. As a leading authority on radiation and heat, Kirchhoff's work was indispensable to Planck's own research. It was Kirchhoff's laws of radiation, which described the behavior of black-body radiation, that would form the theoretical basis for Planck's later discoveries. Kirchhoff's work suggested that the emission of heat by a perfect black body could be explained by a relationship between the temperature and the intensity of the radiation emitted. However, it was clear that Kirchhoff's classical approach could not explain all observed phenomena. Planck, with his meticulous nature, sought to resolve these gaps and deepen the understanding of radiation. It was this intellectual environment, alongside the challenging questions posed by his mentors, that shaped Planck's developing theories and eventually led him to question the classical assumptions of energy distribution in thermodynamics. By the time Planck graduated, he had already distinguished himself as an ambitious and capable scholar. His doctoral thesis, completed in 1879, was focused on the second law of thermodynamics and explored the potential inconsistencies in its classical interpretation. While his thesis did not immediately create a stir in the scientific community, it laid the groundwork for his future contributions. More importantly, the way Planck approached the problems in thermodynamics, questioning the underlying assumptions and seeking to refine existing theories, became a hallmark of his scientific methodology. Although Planck was steadily building a reputation as a promising young physicist, his career did not unfold without challenges. Upon completing his doctorate, Planck faced the daunting task of establishing himself in the competitive academic world. The process of securing a permanent position at a university was often a slow and uncertain one, and Planck faced setbacks in his attempts to gain tenure at various institutions. However, these early challenges did not deter him. In fact, they fueled his determination to succeed and to prove that his innovative ideas could contribute significantly to the scientific community. Despite facing the pressures of competition and the expectations of his peers, Planck maintained his focus on the fundamental principles of physics and his growing interest in the unexplained phenomena within thermodynamics and radiation. His perseverance eventually paid off when, in 1889, Planck was appointed as a professor at the University of Berlin, a position that would provide him with the resources and academic freedom to fully explore his ideas. It was during this period that Planck's intellectual independence truly blossomed, as he began to formulate ideas that would later become the foundation of quantum theory. His work on black-body radiation, in particular, became the focus of his research during these years. While working to explain the phenomenon, Planck began to realize that classical physics was insufficient to account for the observed behavior of radiation, leading him to the radical conclusion that energy could only be emitted or absorbed in discrete quantities, or quanta. This realization marked the beginning of his revolutionary contributions to quantum theory. Max Planck's transition from a student to a groundbreaking scientist was not instantaneous. It was the result of years of careful study, intellectual engagement with his mentors, and the development of his own unique scientific approach. His time at the University of Berlin, his exposure to the works of Helmholtz and Kirchhoff, and the intellectual challenges he faced during his academic career all contributed to his eventual realization of the quantum nature of energy. The challenges he encountered, particularly in securing academic positions and refining his scientific ideas, only strengthened his resolve to find new ways of understanding the physical world. These early struggles and triumphs were instrumental in shaping the path that would lead Planck to become one of the greatest minds in the history of science, and his contributions to quantum theory would forever change the landscape of physics. Max Planck's intellectual growth was largely shaped by the profound influence of his mentors and teachers. One of the most remarkable aspects of Planck's journey is the relationship he had with his educators. From a young age, Planck found himself in the presence of some of the most influential figures in the world of physics. These individuals played a key role in shaping his scientific perspective, encouraging his curiosity, and guiding him through the most formative years of his academic and professional life. During his time at the University of Munich, and later at the University of Berlin, Planck found mentors who not only influenced his technical knowledge, but also inspired his intellectual development. One of the first individuals to leave a lasting impact on Planck was the physicist Hermann von Helmholtz, one of the leading scientific minds of the 19th century. Helmholtz's contributions to thermodynamics, energy conservation, and the development of the theory of nerve impulses made him a towering figure in the field, and Planck had the privilege of studying under him at the University of Berlin. Helmholtz was not just a teacher, but also a source of intellectual stimulation for his students. His ability to bridge the gap between different scientific disciplines, such as mechanics, thermodynamics, and optics, was a profound influence on Planck, who would later apply similar interdisciplinary thinking in his own work. Helmholtz's most significant impact on Planck lay in his teaching of the principle of energy conservation. This principle, which states that energy cannot be created or destroyed but only transformed from one form to another, was a cornerstone of 19th century physics. Planck, under Helmholtz's mentorship, came to appreciate the importance of this principle in understanding the behavior of energy in various physical systems. As Planck delved deeper into the field of thermodynamics, he began to develop an understanding that would shape his future work. Helmholtz's ideas about the conservation of energy were fundamental to the young scientist's later work on radiation and the development of his quantum theory. However, it was not just the knowledge that Helmholtz imparted to him, but the way in which Helmholtz approached science that deeply influenced Planck. Helmholtz was a proponent of rigorous, methodical investigation and the need to question accepted theories, a perspective that resonated with Planck. Helmholtz's influence helped to nurture Planck's own critical thinking and ability to challenge the prevailing ideas in physics. Planck's education also benefited from his exposure to the work of Gustav Kirchhoff, another of his professors at the University of Berlin. Kirchhoff was a leading figure in the study of heat and radiation, and his work on blackbody radiation was especially significant in shaping Planck's scientific thinking. Kirchhoff's laws of radiation, which described how a perfect black body absorbs and emits radiation, were a major contribution to the field of thermodynamics. Planck was initially drawn to Kirchhoff's work, and it was through his studies of Kirchhoff's radiation laws that Planck began to question the classical ideas that dominated the scientific community. While Kirchhoff's laws provided a solid framework for understanding radiation, they were limited in scope. Planck's own investigations into black body radiation would eventually lead him to question the assumptions underlying Kirchhoff's theories. Under Kirchhoff's mentorship, Planck came to appreciate the intricacies of radiation theory, but it was also during his time with Kirchhoff that Planck began to develop his own insights into the subject. Planck's work on radiation was, in many ways, an extension of Kirchhoff's laws, but Planck's approach was notably different. Whereas Kirchhoff's laws could only describe the behavior of radiation in terms of continuous energy distributions, Planck's thinking began to diverge from this classical approach. Planck started to develop the radical idea that energy might be quantized, meaning it could only exist in discrete units, rather than being continuously variable. This insight, which would later become the foundation of quantum mechanics, was born out of his critical examination of Kirchhoff's laws and his desire to explain experimental phenomena that classical physics could not account for. The mentorship and intellectual environment provided by Kirchhoff, who was known for his methodical approach to physics, gave Planck the academic freedom and support to explore ideas that were far outside the mainstream. The guidance of Helmholtz and Kirchhoff was instrumental in shaping Planck's approach to scientific research. However, these two professors were not the only figures to influence him. Planck also benefited from interactions with other renowned scientists, each of whom added a layer of understanding to his growing body of knowledge. One such figure was the mathematician Carl Weierstrass, whose work on mathematical analysis and rigor had a lasting impact on Planck's approach to scientific problems. Weierstrass was known for his meticulous and exacting standards, which influenced Planck's ability to tackle complex theoretical problems with precision and clarity. This emphasis on mathematical rigor became an essential part of Planck's scientific methodology and would later define much of his work. In addition to the direct influence of his mentors, Planck's academic environment at the University of Berlin provided him with the opportunity to engage with a wide range of intellectual ideas and debates. Berlin was a hotbed of scientific discussion during the late 19th century, and Planck was exposed to the work of many other prominent physicists and mathematicians. The intellectual climate at the university was one of constant exchange of ideas, where scientists were encouraged to question accepted theories and to seek new explanations for observed phenomena. This environment helped to foster Planck's intellectual independence and his ability to approach problems from a fresh perspective. Max Planck's ability to absorb and integrate the ideas of his mentors, as well as his intellectual curiosity, enabled him to build upon the work of others and to challenge the prevailing ideas in physics. His mentors, particularly Helmholtz and Kirchhoff, provided him with the theoretical tools and frameworks that allowed him to explore and understand the laws of thermodynamics and radiation. However, it was Planck's critical thinking and his willingness to question established scientific assumptions that set him apart from his contemporaries. Under the guidance of his mentors, Planck's understanding of physics evolved, eventually leading him to the development of his revolutionary quantum theory. The relationship between Planck and his mentors was one of intellectual collaboration, and the lessons Planck learned from them were integral to his success as a physicist. Their influence not only shaped his scientific career, but also instilled in him the mindset that would allow him to make one of the most groundbreaking contributions to science in the 20th century. Max Planck's early academic life and the profound influence of his mentors were crucial factors in his development as a scientist and his eventual revolutionary contributions to physics. His mentorship by Hermann von Helmholtz and Gustav Kirchhoff, along with other intellectual influences during his time at the University of Berlin, provided him with not just knowledge, but also the critical thinking tools needed to challenge conventional physics. His mentor's guidance, along with the intellectual atmosphere of Berlin, shaped Planck's approach to scientific inquiry and provided him with the foundation on which he would build his groundbreaking work on quantum theory. The mentorship of Hermann von Helmholtz, in particular, had a deep impact on Planck's intellectual development. Helmholtz was a towering figure in the world of physics and had made significant contributions to the understanding of energy, thermodynamics, and the conservation of energy. His work bridged the fields of mechanics, thermodynamics, and physiology, and his interdisciplinary approach to science was something that greatly influenced Planck. Helmholtz was not just a teacher but a model for how to approach scientific problems with rigor, systematic thinking, and intellectual flexibility. Under Helmholtz's tutelage, Planck learned to appreciate the importance of energy conservation and how it applied across various physical systems. Helmholtz was also known for his insistence on empirical evidence, and this emphasis on experimental data helped instill in Planck the importance of observation in scientific inquiry. Planck absorbed Helmholtz's rigorous approach to research, but what set him apart was his ability to question established ideas. Helmholtz encouraged his students to think critically, and this was exactly what Planck did when confronted with the prevailing assumptions about energy and radiation. Helmholtz's influence on Planck was profound in that it instilled in him a mindset that was both analytical and open to novel ideas. While Helmholtz focused on classical ideas of energy, Planck began to realize that these theories could not fully explain all phenomena, especially the behavior of radiation. This realization would become a turning point in his scientific journey as Planck began to develop ideas that led to quantum theory. Equally important in Planck's development was his relationship with Gustav Kirchhoff, another influential professor at the University of Berlin. Kirchhoff's work on blackbody radiation, which dealt with the emission of heat from a perfect black body, became the basis for much of Planck's future research. Kirchhoff had established that a perfect black body in thermal equilibrium emitted radiation with a specific spectrum, but his classical approach could not account for the observed phenomena, especially at higher frequencies. It was through studying Kirchhoff's work that Planck recognized the gaps in classical physics. Kirchhoff's laws of radiation were crucial in forming the backdrop for Planck's later contributions. However, while Kirchhoff had set the foundation for understanding radiation, it was Planck who would extend these ideas by introducing the concept that energy could only be emitted or absorbed in discrete amounts. At this point, Planck's intellectual independence began to shine through. While Kirchhoff's laws were instrumental in explaining many aspects of radiation, they left unanswered questions, particularly regarding the spectral distribution of radiation from a black body. Planck was driven by the desire to resolve these issues, and it was through this pursuit that he began to entertain the idea that classical physics might not have all the answers. He realized that the continuous nature of classical physics could not explain the observed radiation patterns, particularly at high frequencies, as seen in the ultraviolet catastrophe. This was a turning point that would lead to his radical new approach to energy and matter. Planck's introduction of quantization, proposing that energy could be emitted only in discrete units, or quanta, marked the beginning of the quantum revolution. This idea, which was initially met with skepticism, would eventually transform our understanding of the universe at the smallest scales. The intellectual environment in Berlin also played a significant role in shaping Planck's scientific thinking. The city was a vibrant center of scientific activity during the late 19th century, home to some of the most brilliant minds in physics and mathematics. The University of Berlin, where Planck spent a significant portion of his academic career, fostered an environment where ideas were debated, challenged, and refined. The faculty at Berlin, including Planck's mentors Helmholtz and Kirchhoff, encouraged independent thought and critical inquiry, pushing students to not only understand existing theories but also to ask new questions and develop fresh approaches. This intellectual environment was critical in helping Planck develop the mindset needed for groundbreaking scientific discovery. In addition to his mentors, Planck was also influenced by his exposure to the broader scientific community. During his time in Berlin, he interacted with leading scientists of the time, engaging in intellectual discussions that allowed him to broaden his understanding of physics. These interactions helped refine his own ideas and motivated him to think beyond the confines of classical physics. One of the most important aspects of Planck's intellectual development was his ability to synthesize ideas from various fields, including thermodynamics, statistical mechanics, and electromagnetism. This interdisciplinary approach would later prove essential in the development of his theory of quantum mechanics. The significance of Planck's early years, particularly his time in Berlin, cannot be overstated. It was in Berlin that Planck's scientific foundation was solidified, and it was here that he began to question the assumptions of classical physics. Through his relationship with Helmholtz and Kirchhoff, Planck was introduced to the most advanced ideas in physics at the time, but it was through his own critical thinking that he was able to take these ideas further. The guidance of his mentors provided him with the tools and frameworks necessary to approach complex problems, but it was Planck's intellectual independence that allowed him to break new ground. His ability to question established theories, challenge classical assumptions, and develop new methods for understanding the natural world set him on a path toward revolutionary discoveries that would forever change the course of physics. Max Planck's scientific career was not defined solely by his relationships with his mentors or the academic environment in which he worked. It was also shaped by his persistence, his intellectual courage, and his willingness to question the status quo. Planck's relationship with Helmholtz and Kirchhoff was instrumental in shaping his approach to scientific inquiry, but it was his own independent thought and the intellectual challenges he faced that ultimately led him to discover the quantum nature of energy. His work, particularly in the field of black-body radiation, would lay the foundation for the development of quantum mechanics and lead to a new understanding of the physical world. Planck's early academic years were filled with challenges, intellectual engagement, and breakthroughs, and they were the crucible in which his revolutionary ideas were formed. Max Planck's journey toward becoming one of the most influential scientists in history was deeply influenced by his early academic experiences and intellectual environment. As a student, Planck exhibited an intense fascination with the mysteries of the universe, particularly in the realms of thermodynamics, radiation, and the emerging field of quantum mechanics. His early curiosity was further fueled by his exposure to cutting-edge scientific concepts and the works of leading physicists of the time, including figures like Helmholtz and Kirchhoff. As Planck's career progressed, he faced numerous challenges that would test his intellectual resolve and scientific curiosity. Through his experiences, Planck's eventual breakthrough in quantum theory came from a blend of intellectual exploration, rigorous mentorship, and a willingness to challenge the accepted paradigms of his time. Max Planck's early fascination with physics was not merely a passive interest. From a young age, he sought to engage with the fundamental questions of how the universe works. Born into an academically inclined family, his childhood was steeped in intellectual discussions. His father, Johann Planck, a respected professor of law, and his mother, Emma Patzig, fostered an environment that encouraged critical thinking and an appreciation for knowledge. Planck's early education was strongly rooted in this atmosphere of intellectual curiosity, and from the outset, he showed an eagerness to learn beyond the ordinary curriculum. This was a time when traditional physics, primarily governed by Newtonian mechanics, was seen as the prevailing and sufficient explanation of physical phenomena. However, Planck's early exposure to the works of physicists such as Helmholtz, Kirchhoff, and Faraday fueled his desire to uncover deeper truths about the nature of energy, heat, and radiation. During his time at the University of Munich, and later at the University of Berlin, Planck encountered the intellectual giants of his time. At Munich, he began his formal study of physics and came into contact with influential scientists. However, it was at the University of Berlin where Planck's intellectual path truly diverged. His mentors, such as Hermann von Helmholtz and Gustav Kirchhoff, were instrumental in shaping his scientific approach. Helmholtz, a professor of physics and physiology, had made foundational contributions to the fields of thermodynamics, energy conservation, and the science of hearing. Helmholtz's theories emphasized the principle of the conservation of energy, a cornerstone of 19th-century physics. He was also keen on exploring the connection between experimental observations and theoretical models, a methodology that resonated with Planck. His exposure to Helmholtz's work gave Planck a deep understanding of the laws of thermodynamics, which would later influence his theories on radiation and energy transfer. While Helmholtz's influence was undoubtedly profound, it was Planck's exposure to the works of Gustav Kirchhoff that would have the most direct impact on his scientific career. Kirchhoff's work on black-body radiation was groundbreaking at the time and laid the foundation for much of Planck's future research. Kirchhoff had formulated a set of laws governing radiation emitted by idealized objects known as black bodies. A black body, according to Kirchhoff, would emit radiation that could be measured and modeled mathematically, and its spectrum would depend on its temperature. However, Kirchhoff's theory was incomplete in explaining the radiation emitted by a black body at high frequencies. It was this gap in classical physics that spurred Planck to develop his own ideas, eventually leading him to his revolutionary insights into the quantization of energy. In studying Kirchhoff's laws of radiation, Planck began to recognize that there was something more fundamental that classical physics could not explain. Planck observed the discrepancies between Kirchhoff's radiation laws and the experimental data, particularly in the realm of high-frequency radiation. This observation marked the first step toward Planck's realization that the classical theories of energy distribution were insufficient. Planck's exploration of this issue would eventually lead him to question the continuity of energy transfer, a principle that had been widely accepted in physics. This questioning would lead Planck to formulate the concept that energy was not emitted or absorbed in continuous amounts, but rather in discrete units or quanta. This realization was the turning point in his intellectual journey, leading to his formulation of the quantum theory of energy. Throughout his academic journey, Planck was also influenced by the intellectual environment at the University of Berlin. Berlin was a hub of scientific thought, and Planck was exposed to the work of many prominent figures in the world of physics. The vibrant academic atmosphere provided Planck with the freedom to explore new ideas and challenge the status quo. The university's emphasis on rigorous scientific methodology, grounded in empirical evidence and logical deduction, encouraged Planck to question established theories and seek out new explanations for the observed phenomena. This environment allowed Planck to engage in thoughtful debate with other scientists, pushing the boundaries of traditional physics. One of the most significant aspects of Planck's academic development was his ability to combine his theoretical understanding of thermodynamics with practical, experimental observation. At the time, thermodynamics was one of the most well-established fields in physics, and Planck's understanding of it formed the basis for much of his later work. His early work focused on understanding the fundamental laws of thermodynamics and radiation, but it was his ability to synthesize these concepts with experimental data that set him apart from other scientists. His practical approach to physics allowed him to recognize the limitations of classical theories and inspired him to pursue new ideas. As Planck's academic career advanced, he began to encounter challenges that pushed him to refine his understanding of the physical world. One such challenge was the inability of classical physics to explain the behavior of high-frequency radiation, a phenomenon that had been observed in experiments but could not be accounted for by existing theories. The so-called ultraviolet catastrophe, which predicted an infinite amount of radiation at short wavelengths, stood in stark contrast to the actual experimental results. This paradox motivated Planck to rethink the assumptions underlying classical physics and led to his groundbreaking hypothesis that energy is quantized. Planck's breakthrough came in 1900 when he proposed that energy could only be emitted or absorbed in discrete units, or quanta. This idea was initially met with skepticism, as it challenged the very foundations of classical physics. However, Planck's quantization hypothesis was later validated by experimental data and became the cornerstone of quantum theory. His work laid the groundwork for the development of quantum mechanics, a field that would later be expanded by scientists such as Albert Einstein, Niels Bohr, and Werner Heisenberg. The significance of Planck's work cannot be overstated. His contributions to the development of quantum theory revolutionized our understanding of the microscopic world and laid the foundation for the technological advancements that followed. The idea that energy is quantized opened the door to new theories of atomic structure, molecular chemistry, and particle physics, which have had a profound impact on fields ranging from materials science to computer technology. Max Planck's early intellectual influences, particularly his exposure to the works of Helmholtz and Kirchhoff, were instrumental in shaping his scientific career. These influences, combined with his ability to synthesize theoretical knowledge with empirical observation, enabled him to challenge classical physics and develop the quantum theory of energy. Planck's intellectual journey was marked by a series of challenges, each of which helped refine his thinking and guide him toward groundbreaking discoveries. His work not only reshaped the field of physics but also had a lasting impact on the scientific community as a whole, revolutionizing our understanding of the natural world at its most fundamental level. Max Planck's path to scientific brilliance was a product of not just his inherent intellectual curiosity, but also the mentorship he received from some of the most prominent scientists of his time and the scientific environment in which he was immersed. His journey from a student with an insatiable curiosity about the physical world to the father of quantum mechanics is a story of academic rigor, persistence, and innovation. The third keynote focuses on the challenges Planck faced in his early career and how he overcame them to establish himself as a groundbreaking scientist in the emerging field of theoretical physics. When Planck began his academic career, the scientific landscape was dominated by classical physics, particularly Newtonian mechanics and thermodynamics. The laws of thermodynamics, which dealt with the relationship between heat, energy, and work, had been firmly established, and the scientific community was confident in the stability of these principles. Yet, as Planck advanced in his studies, he began to recognize certain discrepancies in classical theories, particularly when it came to the behavior of radiation. The gap between theoretical expectations and experimental data, especially regarding high-frequency radiation, became an intellectual puzzle that classical physics could not resolve. It was these gaps in existing theories that would fuel Planck's determination to find a solution, and it is through his relentless pursuit of answers to these puzzles that he began to shape his own revolutionary ideas. One of the earliest and most significant challenges that Planck faced was in the study of blackbody radiation. Blackbodies, by definition, are objects that absorb all the radiation that falls upon them and emit radiation at a characteristic spectrum depending on their temperature. While Kirchhoff had developed laws to describe blackbody radiation, these laws could not explain the observed behavior at short wavelengths, an issue known as the ultraviolet catastrophe. Classical physics predicted that at higher frequencies, shorter wavelengths, radiation would increase without bound, leading to an infinite amount of energy, which obviously contradicted experimental observations. The mathematical models at the time could not account for this discrepancy, and this paradox was one of the primary problems Planck aimed to address. Planck's first attempt to resolve this paradox was through the application of classical statistical mechanics. While he was aware of the inadequacy of existing theories, Planck initially approached the problem by extending the current understanding of thermodynamics and energy distribution. However, despite his rigorous calculations, classical methods did not provide a satisfactory answer. It was in this moment of intellectual frustration that Planck began to question the underlying assumptions of classical physics. He realized that, in order to resolve the issue of black-body radiation, it might be necessary to rethink the very nature of energy. It was not enough to simply apply classical mechanics to the problem. Planck needed to introduce a new concept, one that was more fundamental and could better explain the observations. The breakthrough came in 1900 when Planck proposed that energy was not emitted or absorbed in a continuous manner as classical physics suggested, but in discrete amounts, or quanta. This idea, which later became known as the concept of energy quantization, was revolutionary because it directly challenged the accepted view of energy as a continuous entity. To justify this hypothesis, Planck introduced a new constant, now called Planck's constant, to describe the relationship between the frequency of radiation and the energy quanta. This constant was a mathematical expression of the quantized nature of energy and provided a means of calculating the energy levels associated with electromagnetic radiation. Planck's introduction of quantization was a radical departure from classical physics and laid the foundation for the development of quantum mechanics. However, Planck's revolutionary idea was not immediately accepted by the scientific community. At first, Planck himself was reluctant to fully embrace the implications of his own discovery. He regarded his idea of quantized energy as a mathematical tool rather than a fundamental principle of nature. Planck believed that his theory was merely a temporary solution to a specific problem in black-body radiation, not a new way of understanding the universe at a fundamental level. Despite his initial reservations, Planck's work soon gained traction among other physicists, particularly Albert Einstein, who used the concept of quantized energy to explain the photoelectric effect. Over time, the idea of quantization would become one of the cornerstones of quantum theory, fundamentally altering the way scientists understood energy, light, and matter. The acceptance of Planck's theory was not immediate, and he faced significant skepticism from many of his contemporaries. Classical physicists, particularly those who adhered to the idea of continuous energy, found it difficult to accept that energy could be quantized. The notion that energy could be divided into discrete units seemed counterintuitive, and Planck's concept of energy quanta was initially viewed with suspicion. However, the experimental successes of quantum theory, including Einstein's work on the photoelectric effect and Niels Bohr's model of the atom, gradually convinced the scientific community that Planck's idea was more than just a mathematical tool, it was a fundamental feature of the physical world. In addition to the intellectual challenges that Planck faced, his career also presented him with significant personal and professional obstacles. As a young academic, Planck struggled to secure a permanent position at a university. Although he had a strong academic record, he faced intense competition from other brilliant young scientists. It wasn't until 1889 that he was appointed to a professorship at the University of Berlin, where he would remain for much of his career. Even after securing this position, Planck continued to face professional pressures, particularly as he pursued his research into radiation and energy. His work was often at odds with the prevailing scientific theories, and he faced resistance from colleagues who were deeply invested in classical physics. Despite these challenges, Planck remained dedicated to his research and was resolute in his belief that a new understanding of energy was necessary to explain the discrepancies in the existing models. In his personal life, Planck also endured significant hardships. He suffered the loss of his first wife in 1909, which was a devastating blow to him. Despite these personal tragedies, Planck continued his work with unwavering focus. His resilience in the face of both personal and professional challenges is a testament to his determination and commitment to scientific discovery. Planck's ability to persevere in the face of adversity and his willingness to question the accepted wisdom of his time were key factors in his success. The challenges that Planck faced in his early career were not just intellectual, but also personal and professional. However, through his persistence and intellectual bravery, he was able to navigate these obstacles and make groundbreaking contributions to the field of physics. Planck's work on black-body radiation and his introduction of energy quantization marked the beginning of the quantum revolution. His theories provided the necessary framework for the development of quantum mechanics, a field that would later be expanded upon by physicists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. Planck's ability to confront the scientific challenges of his time with intellectual rigor, creativity, and perseverance established him as one of the most influential scientists in history, and his work continues to shape our understanding of the universe today. Max Planck's transformation from a student to a groundbreaking scientist was deeply influenced by pivotal moments during his academic journey. These moments were not just about acquiring knowledge, but also about Planck's intellectual awakening, where he began to question established ideas and challenge the status quo. His transition into a groundbreaking scientist was a gradual process, marked by his deepening fascination with the concept of energy and its behavior, particularly in thermodynamics and radiation. Throughout his academic years, Planck's curiosity was nurtured by the intellectual environment around him, particularly the teachings of his mentors. At the University of Berlin, Planck encountered some of the leading scientists of the time. These relationships not only helped refine his understanding of existing scientific theories, but also encouraged him to push beyond the boundaries of classical physics. Under the mentorship of figures like Hermann von Helmholtz and Gustav Kirchhoff, Planck was exposed to new scientific ideas that would shape his thinking. Helmholtz's work on energy conservation and Kirchhoff's contributions to radiation laws provided a foundation for Planck's own later work on black-body radiation. These ideas, while important, were incomplete in explaining certain phenomena, especially at high frequencies of radiation, which was where Planck began to diverge from classical physics. During his studies, Planck encountered a crucial intellectual puzzle in the form of black-body radiation. Classical physics, based on the principles of thermodynamics, could not explain the discrepancies in the radiation spectrum of a black body at shorter wavelengths. The ultraviolet catastrophe predicted that the radiation intensity would rise to infinity at short wavelengths, a result that was experimentally contradicted. It was at this point that Planck's intellectual curiosity led him to challenge classical assumptions and seek a new way to explain these observations. His initial solution was radical. Instead of energy being continuously distributed, he proposed that energy could only be emitted or absorbed in discrete units, or quanta. This revolutionary idea laid the groundwork for quantum theory. The impact of Planck's theory was profound, not only because it solved the immediate problem of black-body radiation, but also because it opened the door to a new understanding of the physical world. Energy, according to Planck, was not a continuous flow but rather a discrete quantity. His introduction of Planck's constant, a fundamental physical constant, was a mathematical expression of this new idea and would later become one of the cornerstones of quantum mechanics. This concept of quantized energy challenged centuries of established thinking in physics, moving away from the deterministic nature of classical mechanics to a probabilistic view of the atomic world. Although Planck himself was initially hesitant to embrace the full implications of his work, his discovery marked a paradigm shift in the understanding of energy and radiation. The intellectual climate at the University of Berlin was crucial in shaping Planck's development. The university's reputation as a center of scientific thought provided him with the opportunity to interact with leading minds of the time, engage in intellectual debates, and contribute to the ongoing scientific discourse. The freedom to explore new ideas and challenge traditional beliefs was an essential aspect of Planck's intellectual environment. His ability to navigate and contribute to this scientific landscape was a key factor in his eventual success. Planck's journey from student to scientist was not linear, but rather a complex process of intellectual discovery, mentorship, and personal perseverance. His ability to question and challenge established scientific norms laid the foundation for his future contributions to quantum theory, making him one of the most influential physicists in history. Max Planck's transition from student to scientist was defined by his intellectual independence and his ability to make revolutionary contributions to physics. His early fascination with the physical world evolved into a deeper exploration of energy, radiation, and the fundamental laws of thermodynamics. As he progressed in his academic journey, Planck began to question the established scientific paradigms of his time, eventually leading to his groundbreaking work in quantum theory. This period of intellectual growth was not without challenges, but it was precisely these challenges that propelled him toward a new understanding of the universe. Planck's early education set the stage for his later discoveries. His studies at the University of Munich and the University of Berlin exposed him to the most advanced scientific ideas of the time. While his education was rooted in classical physics, it was during his time in Berlin that Planck began to engage deeply with the emerging field of thermodynamics. Under the mentorship of prominent figures like Hermann von Helmholtz and Gustav Kirchhoff, Planck's understanding of the laws of energy conservation and radiation grew significantly. Helmholtz's work on the principle of energy conservation and Kirchhoff's laws of radiation laid the foundation for Planck's future research. These influential figures not only provided Planck with the theoretical tools to understand existing scientific concepts, but also encouraged him to think critically and to explore ideas that went beyond the established frameworks. However, it was not until Planck encountered the problem of black-body radiation that his intellectual journey took a decisive turn. Classical physics, based on the laws of thermodynamics, could not explain the observed behavior of radiation emitted by a black body at high frequencies. This discrepancy, known as the ultraviolet catastrophe, presented a profound challenge to existing theories. While classical physics predicted that radiation intensity would increase without bound at short wavelengths, experimental data showed that this was not the case. Planck's intellectual curiosity led him to seek a solution to this paradox, and in doing so, he proposed a radically new idea. Instead of assuming that energy was emitted or absorbed continuously, Planck introduced the concept that energy was quantized, emitted in discrete units or quanta. This hypothesis was a revolutionary departure from classical physics and marked the beginning of Planck's contributions to quantum mechanics. His concept of energy quantization, which was initially proposed to explain black-body radiation, later became one of the cornerstones of quantum theory. Planck introduced a new constant, now known as Planck's constant, which mathematically expressed the relationship between energy and frequency. Although Planck himself initially viewed his work as a mathematical solution to a specific problem, his discovery laid the groundwork for future developments in quantum mechanics. Planck's theory demonstrated that energy was not a continuous flow but a series of discrete units, forever altering the understanding of energy and radiation. The impact of Planck's work on quantum theory was profound. While his idea of quantized energy was met with initial skepticism, it eventually became a fundamental aspect of modern physics. His discovery of the quantization of energy influenced other physicists, including Albert Einstein, who used Planck's concept of energy quanta to explain the photoelectric effect, and Niels Bohr, who applied the concept to his model of the atom. Planck's work directly challenged the deterministic view of classical mechanics and laid the foundation for the probabilistic nature of quantum mechanics. It marked the shift from a view of the universe governed by continuous laws to one that embraced the discrete, probabilistic nature of atomic and subatomic processes. Planck's ability to question established scientific theories and propose new ideas was a testament to his intellectual rigor and independence. He did not simply accept the scientific consensus, but sought to understand the deeper mechanisms behind the observed phenomena. His work was not only a response to the immediate scientific challenges he faced, but also an invitation to reconsider how the universe operates at its most fundamental level. The intellectual climate at the University of Berlin, combined with the mentorship of figures like Helmholtz and Kirchhoff, provided the ideal environment for Planck to develop his ideas and make lasting contributions to the field of physics. Through his struggles with classical theories and his eventual breakthrough in quantum theory, Planck redefined the landscape of modern physics. His work opened new avenues of exploration and inspired future generations of physicists to delve into the strange and fascinating world of quantum mechanics. Planck's ability to overcome intellectual and scientific challenges, along with his unwavering commitment to seeking truth, cemented his place as one of the most important scientists in history. His legacy continues to shape the way we understand the fundamental nature of the universe. Max Planck's transition from student to groundbreaking scientist was marked by the development of his own intellectual framework, which would eventually lead him to question existing theories and make revolutionary contributions to the field of physics. One of the key factors in this development was his fascination with the concept of energy and his growing desire to understand the underlying laws governing the universe. As Planck progressed in his studies, he encountered intellectual challenges that would ultimately lead him to challenge the established scientific paradigms of his time. His ability to embrace these challenges, confront complex scientific questions, and remain dedicated to seeking answers became the foundation of his future breakthroughs. During his academic years at the University of Munich and later at the University of Berlin, Planck was deeply immersed in the latest scientific ideas. His early academic pursuits were focused on understanding thermodynamics, the science of energy and heat. It was here that Planck's exposure to the work of influential scientists like Hermann von Helmholtz and Gustav Kirchhoff played a crucial role in shaping his understanding of energy conservation and radiation laws. These mentors not only helped Planck refine his grasp of the concepts, but also encouraged him to think critically about the limits of classical theories. Helmholtz's work on energy conservation and Kirchhoff's laws on radiation served as the intellectual bedrock for Planck's own research. However, it was the problem of black-body radiation that served as a turning point in Planck's intellectual journey. The prevailing scientific understanding of radiation, based on classical thermodynamics, was unable to explain the observed behavior of radiation emitted by black bodies at high frequencies. The ultraviolet catastrophe, as it came to be known, predicted that radiation would increase without bound at short wavelengths, contradicting experimental data. This paradox challenged the very foundations of classical physics, and it was in this context that Planck's curiosity pushed him to explore new ideas. Rather than relying solely on classical mechanics to explain the problem, Planck began to consider whether the energy emitted by a black body might not be continuous, as traditionally thought, but instead quantized, emitted in discrete units. Planck's idea of quantized energy was a revolutionary departure from classical physics. By introducing the concept of quanta, Planck was able to reconcile the discrepancies in the observed radiation spectrum, providing a solution to the ultraviolet catastrophe. Planck's mathematical approach, which included the introduction of a constant now known as Planck's constant, was designed to express the relationship between energy and frequency in the context of black-body radiation. This idea was initially viewed with skepticism by many in the scientific community, but Planck's intellectual independence and his willingness to challenge the classical understanding laid the groundwork for future developments in quantum theory. Although Planck himself was initially reluctant to fully embrace the implications of his work, his theory of energy quantization soon gained widespread recognition. This shift in thinking about energy was transformative, not only in the field of thermodynamics but also in the broader landscape of physics. Planck's concept of discrete energy units challenged the classical view that energy was continuous, and instead opened the door to the probabilistic and quantized nature of the atomic world. His work directly influenced other physicists, most notably Albert Einstein, who used the concept of quanta to explain the photoelectric effect, and Niels Bohr, who incorporated Planck's ideas into his model of the atom. The influence of Planck's work extended far beyond his own time. His ideas were fundamental to the development of quantum mechanics, a theory that would revolutionize our understanding of the behavior of particles at the atomic and subatomic levels. Planck's discovery marked a paradigm shift in the way scientists understood the physical world, moving from a deterministic framework to one that embraced uncertainty and the probabilistic nature of quantum systems. His ability to push the boundaries of classical physics challenged the assumptions of his contemporaries and develop an entirely new way of thinking about energy established him as a pivotal figure in the history of science. In addition to his scientific accomplishments, Planck's personal qualities were crucial to his success. Throughout his academic career, Planck demonstrated intellectual perseverance and a willingness to engage deeply with complex problems. His dedication to understanding the fundamental laws of nature, coupled with his ability to think critically and independently, allowed him to make groundbreaking contributions to the field of physics. His work on energy quantization not only solved a long-standing problem in thermodynamics, but also laid the foundation for an entirely new approach to understanding the universe at the quantum level. Through his groundbreaking work, Planck forever changed the course of physics and established himself as one of the most influential scientists of the 20th century. Max Planck's intellectual evolution, from a curious student to one of the founding fathers of quantum theory, was marked by numerous pivotal moments. His journey was shaped by not only his academic pursuits, but also his deep-rooted curiosity about the physical world and his willingness to challenge conventional scientific thought. The seventh keynote, focusing on Planck's transition from a student to a groundbreaking scientist, underscores his growing ability to question existing paradigms and forge new paths in theoretical physics. His ability to synthesize his academic training with his intellectual independence laid the foundation for his revolutionary discoveries. Planck's formative years in science were heavily influenced by the intellectual environment at the University of Munich and later at the University of Berlin, where he studied under some of the most prominent physicists of his time. These early years provided Planck with a strong foundation in classical physics, particularly in the fields of thermodynamics and energy conservation. Under the mentorship of Hermann von Helmholtz, Planck developed a deep understanding of energy principles, especially the concept of energy conservation, which was central to 19th century physics. Helmholtz's insistence on empirical evidence and the importance of experimental data provided Planck with a framework for approaching scientific problems with rigor and precision. Similarly, his exposure to Gustav Kirchhoff's work on radiation laws helped shape Planck's early research, particularly in the study of blackbody radiation. Kirchhoff's laws, which describe the radiation emitted by perfect black bodies, formed the basis for Planck's later work on the quantization of energy. Despite his solid foundation in classical physics, Planck soon encountered significant intellectual challenges that would force him to rethink existing scientific models. One of the key challenges came in the form of black-body radiation, a phenomenon that classical physics could not explain. While classical thermodynamics, grounded in the continuous nature of energy, worked well at lower frequencies, it failed at higher frequencies, leading to the ultraviolet catastrophe. This paradox predicted that energy would increase without bound at shorter wavelengths, a result that contradicted experimental observations. It was here that Planck's intellectual curiosity was truly tested. Classical physics had reached its limit in explaining the behavior of radiation, and Planck was determined to find a new approach that could resolve this discrepancy. In 1900, after much deliberation and careful analysis, Planck proposed the radical idea that energy was not emitted or absorbed in a continuous manner, but in discrete units, or quanta. This idea was a direct challenge to the prevailing assumptions of classical physics, which had long assumed the continuity of energy. Planck's introduction of the quantization hypothesis offered a solution to the problem of blackbody radiation, explaining the observed spectrum of radiation without falling into the paradox of infinite energy. His theory posited that the energy of oscillators in a black body could only take on discrete values proportional to the frequency of the radiation. This was a pivotal moment in the development of quantum mechanics, as it marked the first time that the idea of discrete energy levels was seriously proposed. Planck's theory was groundbreaking, but he did not initially see the full implications of his own work. He viewed his hypothesis of quantized energy primarily as a mathematical trick, a temporary solution to a specific problem in radiation theory. Planck himself was reluctant to embrace the idea that the entire fabric of physics might be governed by the concept of quanta. Despite this, his work laid the foundation for the future development of quantum theory, influencing later physicists, including Albert Einstein, who applied the concept of quanta to explain the photoelectric effect, and Niels Bohr, who incorporated Planck's ideas into his atomic model. The intellectual environment in Berlin played a significant role in shaping Planck's ability to confront such challenges. The university's culture of open debate and rigorous scientific inquiry provided Planck with the freedom to explore new ideas and challenge existing theories. This intellectual climate was essential to Planck's growth as a scientist. His ability to navigate the complex scientific landscape of his time and his willingness to question well-established ideas set him apart from his peers. In addition to the guidance of his mentors, the interactions Planck had with fellow scientists and researchers in Berlin helped him refine his ideas and push beyond the confines of classical thought. Planck's ability to break from tradition and think outside the boundaries of established physics ultimately led to his transformation from a promising student to one of the most influential physicists of the 20th century. His work on the quantization of energy opened the door to a new understanding of the atomic and subatomic worlds. His insights into the nature of energy and his development of Planck's constant laid the groundwork for the quantum revolution that would follow. While his theory of energy quantization was initially met with skepticism, it eventually became a cornerstone of quantum mechanics, a field that would fundamentally alter our understanding of the physical universe. Max Planck's journey from student to groundbreaking scientist was defined by his ability to question existing ideas, confront intellectual challenges, and forge new paths in theoretical physics. His transition into the field of quantum mechanics marked the beginning of a new era in science, one that would redefine how we perceive the universe at its most fundamental level. Planck's work not only solved a long-standing problem in radiation theory, but also laid the foundation for the development of quantum theory, which would revolutionize science in the 20th century and beyond. Through his intellectual independence, his perseverance in the face of scientific challenges, and his ability to think critically and creatively, Planck became one of the most important figures in the history of physics.